Section 2.6, freely falling bodies. So in the absence of air resistance, it's found that all bodies at the same location above the Earth fall vertically with the same acceleration. If the distance of the fall is small compared to the radius of the Earth, as long as you aren't too far from the Earth, then the acceleration remains essentially constant throughout the descent. So this is idealized motion. It's called free fall because you are freely falling. And the acceleration of a freely falling body is called the acceleration due to gravity, or in some cases we just call that gravity for short. So gravity, or the acceleration due to gravity, g, has the magnitude of 9.80 meters per second squared, or in math class you may have seen it's about 32 feet per second squared. In this class, we're going to really be working just with this 9.8 meters per second squared. So that's the one that you need to know. This gives you the magnitude of the acceleration. Now, what's the direction of the acceleration due to gravity? Which way does gravity pull objects? It pulls them down, right? If I let go of this tennis ball, it's going to start accelerating downward. So to show the direction of the acceleration, this is g, which we will use other times. It's important to note that this is actually positive. The overall acceleration a is a negative g. Or in other words, the acceleration a in all of our kinematic equations that we saw previously is negative 9.80 meters per second squared. So that's a really useful note. You'll use that on a number of problems. If you can identify something as falling through the air and it doesn't specify that it's somewhere other than Earth, you know the acceleration. That's negative 9.8 meters per second squared. For this chapter, while we're in one dimension, this means that since we're focusing on things falling, instead of using x's, we're going to use y's. So anywhere you see an x in equation, we're going to switch to the y direction just to emphasize that the object is moving up or down as opposed to side to side. All right, so those are the two real changes. And besides that, we'll be able to use those 4 kinematic equations in a number of scenarios. Now, I want to highlight for a moment that it says that all bodies fall at the same acceleration. And if you look at the kinematic equations, you'll notice there's nothing involving mass in those equations. So it shouldn't matter. The time should just depend on what the location they are above the Earth's surface, and then the acceleration, and the acceleration is apparently the same. So I want us to think for a moment, is this something we see, right? If I set up a competition right between a piece of paper and a tennis ball and let these fall, are these going to accelerate at the same rate? Well, the good news is, because this is science, we can try it, right? So I will release them both on the count of 3. So 1, 2, 3. That was not the same at all, right? Not by a long shot. The tennis ball won. Why did the tennis ball win? Is physics broken? The key here is that this only works in the absence of air resistance. And we're going to assume in most cases that we can neglect air resistance. So this will be true, but it's why we don't necessarily see it in our everyday scenario, because in most cases, we do have air resistance around us, and that gets in the way. Now, ways that I could get this better are maybe if I crumpled my paper up into a ball, then we might see a much closer race. There still would be perhaps a bit more air resistance. But what if we could take all the air resistance out? Well, that is in fact what was done by astronauts when they went to the moon. So I'm including in the playlist a video of this, the feather and a hammer, physics on the moon. And so an astronaut dropped a feather and a hammer, one from each hand, and you can see if they actually hit at the same time. It's pretty cool. Oh, please do check it out. It's less than a minute, so it's worth a watch. Right, let's look at a conceptual example, taking advantage of symmetry. Does the pellet in part B strike the ground beneath the cliff with a smaller, greater, or the same speed as the pellet in part A? So here we have part A. The pellet is going up from the cliff with 30 meters per second and then coming down. In part B, the pellet is launched downward from the cliff at 30 meters per second. So I want you to reflect on this for a moment. So go ahead and pause your video to come up with an answer. Right? Did you come up with something? Okay. Well, there's a clue here in the slide in figure C, and that's that it shows the path of A. And we note that when you throw something up or launch something up with an initial velocity of 30 meters per second, then because the acceleration is constant, assuming we don't have air resistance, then it will slow down to a stop at the top, and then it will continue to start to accelerate. It will start to move faster in the opposite direction. It'll have this same acceleration pulling it down, so that at this point at 30 meters per second, it is that speed, right? And so that's the same as if it was flung downward. There's this really nice symmetry here. So it doesn't get any head start by going up, nor does it get delayed. Well, it does get delayed in time, but the speed at which it strikes the ground beneath the cliff or the water is going to in fact be the same. To understand this better, let's look at one more conceptual example. So this is acceleration versus velocity, and you heard me even slip up a little in describing them because it's really tricky to describe the two. So we'll focus in on a coin toss. A coin toss has three parts to the motion of the coin. On the way up, the coin has a velocity vector that is directed upward and decreasing magnitude. It's getting smaller and smaller. At the top of its path, the coin momentarily has zero velocity. And on the way down, the coin has downward pointing velocity with an increasing magnitude. So a negative velocity because it is going down. In the absence of air resistance, does the acceleration of the coin, like the velocity, change from one part to another? This is a really tricky question that I see students, all types of students, wrestle with this. So please pause for a moment, reflect, decide if you are going to stand for yes or no, and why. So go ahead and pause. Okay, I'm gonna trust you did that. Now this one's a tricky one because, especially because the velocity stops at the top. That's really weird. But let's look for a moment at the speed. So when it's going up, it's a positive velocity, but it's a decreasing magnitude. So it's getting slower, right? It's losing speed as it's going up. Well, how can we reduce speed when our velocity is going one way? That means our acceleration needs to be going opposite to that velocity, right? The acceleration is going down. On the way down, the coin has a downward pointing velocity with an increasing magnitude. Well, what's the direction of the acceleration for the speed to be increasing? It needs to be in the same direction as the velocity. So for both the coin going up and the coin going down, the acceleration is pointed down, right? That we have this acceleration going down, and that is true whether it is talking about the coin on its way up or the coin at the end on its way down. Now, what about in the very middle, when the velocity is briefly zero? Does the acceleration turn off and become zero at that point too? It's a tough question. One thing I would offer that might help you is if there was no acceleration when the velocity was zero, then the coin would just hover in the air. There'd be nothing pulling it back down to the earth, so it would just hang out there. It's only if it does have a downward acceleration that the coin would start to move again. So in all cases, the acceleration is going to be down, and it's going to be that constant negative 9.8 meters per second squared. So does it change? No, it does not change. Right? I hope you got some good wrestling there. I'd love to discuss it further if you are interested. Okay, and then let's look at an example with a coin toss, but with some numbers. How long is it in the air? So a football game customarily begins with a coin toss to determine who kicks off. The referee tosses the coin up with an initial speed of 5 meters per second. In the absence of air resistance, was the total time the coin is in the air before returning to its release point. Alrighty, so we already have a picture here, right, where that shows the coin going upward as it's getting flicked up. And so what we want to do is write down what we know. And what I really like for trying to approach this for kinematic problems, for problems involving motion with our standard variables, is I like to make a table like this. This is a table that has all 5 of my kinematic variables. It has the displacement in the vertical direction, y, the acceleration, the final velocity, the initial velocity, and the time. Now, before we can really fill this in, we want to figure out our segment of interest, right? Are we focused on the entire flip of the coin when it's going up and when it's coming down? Well, let's look closely. It says the total time it is in the air before returning to its release point. So this is a little tricky. It looks like we do want the entire up and down. So let's see what we can fill in here to go with this. So the acceleration is the first thing I always want to fill in, and if you write this down, you can get partial credit on an exam because it's that important. Acceleration we know because it is something that is freely moving through the air. My acceleration will be what? Yes, negative 9.8 meters per second squared. That is a 9. Sorry, it's a little blurry there. All right. Anything else that we know here? Well, one thing we have is this initial speed of 5 meters per second. So initial speed is going to go in the v naught, 5.00 meters per second. And really this could be 9.80, excuse me for that. All right, now the other thing we need to add with this initial velocity is the initial velocity going in the positive direction or the negative direction. It is going up, so that is a positive. All right, now within this table, what are we looking for? What do we want to know? Well, notice it's asking about the time. So we want to find out about the time here. So that is where we are headed with this example. Now, as we're looking at this, we do have to look at the fact that we only know 2 of our kinematic variables. We don't know anything about how high it goes, right? Or the velocity there. So there are a couple ways around this, because with these problems, you'll see there are multiple ways you can solve them. One is we could split this motion in half, and instead of considering the entire motion, we could just consider the going up. And the advantage of that is that on the upside, at the very top, what is the velocity? Well, at this point, the velocity is equal to 0. And so we could find the time that it takes to go up, and we could even note that that's going to be the same on either side. So we would just have to, for our total time, it would end up being 2 times the time it takes to rise or to go up. All right, so that would be one approach. The other approach is there is some other information that's tucked into this problem very subtly. And that's that it says, before returning to its release point. So it launches in the air and it comes right back to its release point. If it has returned to its release point, that tells us about one of our variables. What variable does that tell us about? It tells us about the displacement in y, right? We could actually fill in the displacement in y is 0 meters. All right, so that's one of the ways that we can approach this that ends up working pretty well, I think. Actually, the math on that is going to be a little hard. So that may not be the best. Let me explain. So we have, to use this one, it's missing the final velocity. We don't know anything about that. So our equation would be the one that does not have final velocity. So it would be y is equal to v0t plus 1/2 at squared. So we could entirely solve this equation, but because we are solving for t and we have a t and a t squared, that would involve using the quadratic formula. But we could do that. And maybe honestly, I will do that now just to highlight it, to show that it is possible. But if you prefer instead breaking the motion in half and solving for the time it takes to go up and multiplying that by 2, that would work just as well. Okay, so let's take a look here. If we start plugging in our numbers, we would have a 0 is equal to a 5. I'm going to drop my units, times time plus 1/2 times negative 9.8 times time squared. So if I add these to the other side or subtract them to the other side, we are left with, and this is getting really messy, so I'm going to switch to the whiteboard. 9.8, 1/2 of 9.8 becomes actually 4.9. And here I can do my units because it's not too hard. Meters per second squared times t squared plus, or actually, yeah, plus a negative 5 meters per second times time. And this is all equal to 0. So to use the quadratic formula, which this is great to highlight, we note that the form is ax squared plus bx plus c is equal to 0. And then we know that we can solve for x or whatever variable we're interested in with negative b plus or minus b squared minus 4ac, all divided by 2a. And just for reference, here we can stop sharing for a moment. So this is a bit bigger. For reference, you don't need to memorize the quadratic formula because that is inside the front cover, right? That's one of those things that's given to you. It's right here on the bottom, so it's a little hard to see. But there we have it on the bottom. But you do have to know how to use it. So if this is our quadratic formula, we can identify what each of the things are, right? This 4.9 is going to be my A, and this is going to be my B. And because the displacement is 0, C is equal to 0. So that actually simplifies this quite a bit. All right, and then T is my X. So that tells me I can say that the time is equal to negative b, so negative 5 meters per second, plus or minus the square root of b squared, so negative 5 meters per second squared, minus 4ac, where c is 0. So we're going to actually subtract 0 from this. And this is all divided by 2 times a, which is 4.9 meters per second squared. All right. So believe it or not, we are through the worst of this. It's going to get better from here. So notice the negative and negative of the 5 becomes a positive. So I have that my time is equal to positive 5 meters per second plus or minus the square root of 25 meters squared per second squared. And then divided by 2 times 4.9 is actually just going to give me 9.8 again. All right, and notice in the square root, what's my square root of 25? That's just going to be 5. Or since it was 0, we could have just done the square root canceling the square. So this is just going to be 5 meters per second, plus or minus 5 meters per second. And the plus or minus says that there are 2 possible solutions here. This is actually a good thing, believe it or not. We can first check the minus case. If it's minus, we'd have 5 minus 5, we'd get a time of 0. The other option, if we do the plus, is we'd have a time of 10 meters per second divided by 9.8 meters per second squared. And so at that point, we would actually have a number that we could calculate. So 10 divided by 9.8, and that would be 1.02. What would the units there be? Well, if we have meters per second, sorry, this is getting pretty low. If we have meters per second divided by meters per second squared, then most of that will cancel except for the very bottom. The 1 over seconds will be left. So 1 over inverse seconds, actually. So we are left with units of seconds, as we would expect. And we have 2 options here. And that's because it depends on the coin toss. When does the coin toss have a displacement of 0? Well, before the coin gets thrown, the coin is right where it started. And then after the toss, while it's going through the air, after 1.02 seconds, we would then have it right back where it started again. So let's go back to the shared screen so you can see that. All right, so that allowed us to solve for the time. And it's possible that we can solve for other things too. So we could have also potentially approached this to solve for the displacement to the highest point, right? If we want to solve for the maximum height of the coin toss, then we would definitely use the fact that at the top of the motion, the velocity is 0. So that's, excuse me, sorry for that, what was done here. And if you then know the acceleration, the final velocity, the initial velocity, and you want to find this displacement y, then you'll use the equation that does not have time, right? So the equation that does not have time is our final velocity squared plus initial velocity squared plus 2ay. You can rearrange that to solve for the displacement, and that tells you how high the coin got tossed. So this highlights all the different ways you can solve for pieces of information in the problem. For instance, you could use this maximum height to solve for the amount of time it takes to reach that maximum height. And I'll give you a hint, it's going to be exactly half of this 1.02 seconds that we just solved for. So hopefully this gives you some sense of how we can use the fact that the acceleration near Earth is always exactly negative 9.8 meters per second squared. So if you have questions, please feel free to ask away.